This guy is my Nomadic Technologies N150 robot. I previously recorded all the disassembly, reverse engineering, and showed off how I restored functionality to the drive system. This thing's got a cool 2-degree of freedom movement system, plus this turret on top that rotates independently and has an array of 16 ultrasonic rangefinders. In this video, I'm going to be restoring functionality to those. That's my main goal, and I'm gonna add some wireless connectivity so that I can control it without plugging in my PlayStation controller, and hopefully be able to avoid some obstacles and follow a path using only the ultrasonic sonars, plus dead reckoning from the encoders in the steering and the drive motors. I did a little bit more research since I last put a big push into working on this project, and now after putting it down for a while, and I found all of these images of very similar looking Nomadic Technologies robots, but none of them quite exactly like mine. These are all super weird, but honestly really cool. Just all these slight variations of them, mostly black and white with this really old technology. Some of them playing soccer, have crazy big old laptops in their head. They look kind of spooky, almost like they're a AI generated image of what you'd get if you asked for like a robot from the 1970s or something like that. But anyway, just thought these were some cool pictures that were worth sharing. That one had a robot arm on top. But then the only one that I've actually found that looks like mine is this one. This is the only image I've found of the N150 besides my own images that I've posted when I search Google. I get those back now. I realized the transducers on this robot are almost identical to those really old school ultrasonic rangefinders that you would see on those Polaroid cameras that the hipsters carry around, like down to exactly the pattern on the wire mesh protection on the front, identical parts. And I started researching replacement parts for those cameras, and lo and behold, I found this PCB which has a virtually identical layout to the one that's actually in my robot. It's a little bit more modernized. It uses some surface mount components in place of through hole, but I found a datasheet for it, and that really helped me to figure things out. I'm still using this original part, to be clear, but I just kind of think it's hilarious that I was able to find a datasheet for a modern replacement that's meant for a camera, but if I wanted to, I could install this in this late 90s robot and it would work the same as if it were installed in some kind of like Polaroid analog hipster camera. This is the main sonar board and one of the 16 sonar modules from my Nomadic Technologies N150 robot. I'm reverse engineering it to figure out how to interface it with an Arduino, and I'm kind of replacing and updating a lot of the components to get it to work. This robot's about 25 years old and I'm hoping to restore it. But the way that all this works, I figured out. Essentially you have this kind of tan colored daughter board up top, and that's what generates the pulse that goes to the sonar module and reads the signal that comes back. So that board, there's only one of it, and there's 16 sonars all around the circumference of the robot. So these little smaller chips, here, 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 and all around, there's one per header, and those are all relays. So one and only one of them is closed at a time, connecting one transducer at a time to the sonar board right here. These two longer chips are what does the multiplexing. Those share the same 4 inputs, A0, 1, 2, 3, which I have broken out over here going to the Arduino. And depending on what those are, there are 16 possible outputs. So that's what energizes the coil on one of those 16 relays. This blue wire here is the input to the sonar board. That is what tells it to initiate a pulse. And this orange wire is the echo. So that's what gets a high voltage when it receives a signal bounced back off an object. What my Arduino is doing is it's using the 4 multiplexing pins to select which of the 16 sonar transducers to activate. I've chosen this one, obviously. And then it's sending a high signal on this blue line to initiate a pulse. It's waiting until it receives one back on the orange wire, and then the time between that, you can calculate the distance based off the speed of sound. This board is powered externally from 12 volts here, and the Arduino is also powered externally from its own supply there. This chip over here is an I/O expander, which communicates over I2C. That's what these two wires are, and it's taking 3-volt power over those two wires, and then this is its output, which is what the Arduino is telling it to send a signal to pulse the sonar. A couple of reasons I'm using this is because I already have one teensy in the robot, and using an expander like this, I don't have to add a ton more outputs because that one's already kind of full. Although I may end up doing 2 separate microcontrollers anyway because they're both individually doing really timing sensitive things using interrupts and holding functions and such. But mainly during my testing, I found that this pulse signal, it kind of sinks a ton of current, more than I was expecting to. I haven't measured exactly how much, but it causes the voltage to drop way low when I'm just trying to run it directly off one of the Arduino's output pins. And so this I/O expander can actually handle a little bit more current throughput, and it doesn't have that problem, so it's able to trigger this just fine. I've turned off the lights just to show the LEDs pulsing, and you might be able to hear it clicking. Right now I just have it set to pulse about every 2 seconds, I think. So if you look at that bottommost number, it is pretty accurately repeating the distance from my table to my ceiling, about 5 3/4 feet. And then if I put my hand above it, it'll drop to about 2 feet, move it closer, get smaller, further away. Because the multiplexing chip for the LEDs is receiving the exact same inputs as the multiplexing chip for the relays, and the relays are always on when chosen, you'd think that the LEDs would stay always on, but actually the initialized signal coming from that blue wire runs through an inverter chip kind of underneath this corner of that daughter board, and then to the enable pin on the multiplexer with the LEDs. So the effect of that is that they're only on when that initialized signal occurs, and then it turns back off again when the echo comes back. So that means the light is on for the duration that the sound pulse is traveling to and from. The transducer itself is really simple. It doesn't actually use all of these wires. It's just 2 to the membrane part of the transducer itself, and then only 1 actually is split in parallel across both those current limiting resistors for the 2 LEDs. There were a few mechanical things to address before I could totally get started testing. Mainly the original tires had just crumbled away. They were totally brittle. Originally they were some kind of rubber, but had just hardened and cracked over the years. So I printed some new ones out of hard TPU, about the hardest my local print shop had, to hopefully have some good durability. And after a few iterations, I got those to fit more or less okay. So we'll see how long they last. Here's a shot of the limit switch for the steering motors. That one works just fine, and I got it to work for the homing sequence. The turret has a similar one that I didn't get to work yet. Here's the finished sonar board, all soldered up on a proto board, and some modifications to the original motor control board for the encoders and a 3D printed bracket. I also soldered together a similar board for the ESP32. All it's got is the power connection, the I2C connection, and a single linear regulator under it to step down the 12 volt. A look at the top of the robot. This enclosure has the ESP32, and the only reason it's external is so that the Wi-Fi antenna gets a good signal. Otherwise, inside the turret, it's kind of a big Faraday cage. So it's got power wires running in through there, and this multi-conductor cable is how it's got the I2C connection. Over here are just some USB extensions that go to the other 2 microcontrollers inside, so I can flash code onto them without unscrewing the top every time. The emergency stop and the main power switch work the same as before, plus I can optionally plug in my PS2 controller there to manually control it without Wi-Fi. Some kind of hardware failure that I've yet to diagnose is preventing the limit switch in the turret from working. So for now I just have a Sharpie mark that I've been manually aligning with that every time to get a consistent 0. the steering wheels themselves do zero properly. So I just manually align that while it's off. And then when I turn it on, it knows the offset between that and the steering zero, so it's able to align it. So as of right now, it is functional with pretty much all of the original hardware. Besides that limit switch, I also have not yet figured out these bumper switches, which are these red rings around the circumference. But all of the drive stuff is working, all of the sonar stuff is working. It's using the original motor drivers, power distribution, slip ring, sonar driving board, and sonar multiplexing board. But other than that, I've essentially rebrained everything. All I removed from it was this original main board that's replaced with a couple of modern microcontrollers. And I pulled out this old radio that I never quite got to work. It does have Wi-Fi now, so I don't think that even existed when this robot was built originally. Here's the setup under the hood. On the previous video of this robot, I had only this main board, which takes that big multi-pin connector that comes from the slip ring, and that goes down to the bottom of the robot to the power distribution and the 3 motor drivers. That also, I've added some more connections on here. So now that is talking to the motor encoders and to the limit switches. Also, that has my connector that goes eventually up and out to where I plug in the PS2 controller. So I can control it directly through that. And it has a DC-DC converter plus a control for the, it breaks out the emergency stop, which goes down to the power distribution board in the bottom. This new board is responsible for driving the sonar signals. So it's pretty much only connected to the sonar board, and this chip is an I/O expander that I'm essentially just using as a solid state relay. These two are connected through this little I2C hub. So one connection per microcontroller, and the third one goes up and out to the ESP. Those are the power lines for the ESP, that red and black one, going over to this 12 volt power distribution. That just comes from the 12 volt battery, also going down through the slip ring underneath this central board. This is the original multiplexing board for the sonar module. This tan PCB is what drives the signals and amplifies the echo. But then all these chips around here are basically relays that decide which of the 16 transducers is actively hooked up to the electronics. So you don't need 16 of this tan board. And I've plugged in all 16 of them in about the only way they would fit. And then that's talking to the sonar driving microcontroller. The third one, the ESP on the outside, all that's doing is communicating data over Wi-Fi. That's it. So the main 12 volt power, which comes from a battery in the bottom up through a slip ring, comes through a hole below this board, out through these 2 wires, and up through that main switch, which is how I cut it on and off, and back down into this board where it's distributed to everything that needs 12 volt. All of these little sub boards have their own regulator. You can see it right there to step it down to 5 that the microcontrollers need. And these last 2 lines go over to the ESP on the outside. This guy has a little bit of a nicer switched regulator. I mainly went with this 2 microcontroller architecture because each one is independently doing some very time-sensitive tasks that I don't want to interfere with each other using interrupts and delays. This one is reading all the motor encoders, which work using interrupts. And this one is dealing with the sonar that it waits until it receives the echo, which is essentially a holding function. So I don't have to worry about these 2 sensitive timing functions messing with each other. This hub is completely passive. It does have an LED that shows when it's on, but no pull-up resistors or anything. I'm using nothing but the internal pull-ups on the microcontrollers, and I haven't had any signal issues, even though these wires are fairly long. and I2C normally doesn't like long connections. All of these parts are just on some 3D printed mounts that bolt into all these existing threaded holes wherever convenient. And I will say that this bolt pattern, whatever this is, it kind of drove me insane trying to figure it out, because none of these are square, none of these seem to have any kind of radial symmetry, there's no pattern, I don't get what's going on, so I just measured some and fit them where I could. If you're interested in seeing all the mechanical and electronics in the base, I have a separate video that went into that. It's kind of got a crazy gear and pulley system that drives all the rotation. Here's a clip of the homing sequence. As I turn it on, you'll see first the steering motor turns in one way a short distance in case it starts out on the limit switch. Then it goes back and turns the other way until it hits the limit switch, which will happen in a second here. There it did. And then the turret moves to match the position of the steering axis. So it overshot it there, and then it's correcting. It is a closed loop PID control doing that, and I'm sure my gains are not tuned super well, so it does kind of overshoot, but it follows it a little bit better in practice when I'm only making short adjustments instead of a sudden step. Here is the GUI that I made just for this robot. Over on the left are some variables for debugging. You can pretty much ignore that. The top corner X and Y here are the Cartesian coordinates that it obtains through dead reckoning in feet. And the y-axis there is defined as straight ahead from its starting position along this axis. The red lines around the circumference are the distance that each ultrasonic transducer is measuring. There are 16 of those. The blue one is just the one that I've defined as 0, then 1, 2, 3, etc. And the green line is the direction of the steering axis of the robot, so that can move independently from the turret with the circumferential ultrasonic transducers. But for now I have a PID loop that's trying to match turret 0, or rather transducer 0, with the direction of steering. I also have my phone duct taped to the top, which is facing in that direction too, so it should always be having the camera pointed in the direction of travel. Down here, that just shows which arrow keys I'm pressing to steer it. They will light up green when I press forward, back, left, right. And so now I'm going to try to navigate this robot using only this GUI, only the dead reckoning and the sonar data. Okay, so a couple of things went wrong on that first attempt, which I believe I have corrected and I've reset. The sonar echoing was timing out when it was near the couch. It just wasn't getting a good reflection off that soft surface. And the timeout was set to 2 seconds, which if that is happening on 3 or 4 of the transducers, that's like a 10 to 12 second period that also, the way my code works, it stops updating the signals it receives and sends as well, because that just stops all of the code. So I've drastically reduced that timeout, and I've put the cell phone in a different room to where hopefully it gets a better signal between both the robot and this computer that I'm running on. So let's try again. Also, by the way, I've switched to my GoPro for the forward-looking camera on the robot, since the phone is positioned to optimize the Wi-Fi signal. So now I've got a lot of room behind me in this room, I can see, and just one beam looking through that narrow doorway. And again, that blue line should be more or less right where the camera is pointing. So I'm kind of just trying to steer towards where there's open space. And I can no longer see it around the corner. So I do know it's going to need to make a left turn here shortly. And now I see space opening up to my left. I'm seeing 10 feet, 9 feet. Let's turn towards that until I get a good long reading on my blue line. A little more, maybe. And now I'm getting, okay, so there's a wall behind me for sure. That's my front door. Now I'm probably going to be approaching the couch. I still seem to have a lot of space in front of me. Okay, space is opening up slightly to the right, so I want to avoid the couch. Let's steer a little bit to the right. 13 feet ahead, that looks good. 10. Okay. I'm going to steer slightly to the right. I know I'm in a pretty narrow little zone between the couch and the bookshelf. Maybe a little more to the left. And my plus y-axis, straight following the y-axis, should be roughly the right direction, as I expect. Okay, I just saw a long reading this way. Let's turn a little bit. Okay, I don't think I've run into anything yet. I'm seeing a lot of space behind me and some obstacles to my left and right. Also, when these sonars time out, which is happening down here intermittently, they just show a 0 for the line. So when you see a line disappear, it did not get a reflection. So that's probably happening against the soft couch. My house is not big enough to just run out of space. It should reflect off a wall eventually unless it hits a soft object. Okay. Look at that. I kind of think I'm in a sort of box shape based on what these lines are saying. And this is to scale, by the way, these lines. So, okay, there's clearly something in front of me. Have I made it to the kitchen? I think I'm probably... Let's go right up until... Yep, there's definitely something in front of me. Okay, I'm kind of boxed in here. I think I'm in the kitchen now, because I see a sharp corner there, and I'm probably more to the left side of the kitchen. Back here is around where the trash cans are, and I see a long space behind me, which is the hallway I just came down. I'm about 30 feet forward of where I started and 5 feet to the right. That seems about right, based on knowing my house. I'm going to try to look at the trash cans. Trash cans should be right about here. I think I'm looking at the trash cans now. Well, probably a little bit more this way. Yeah, hopefully you can see the trash cans. Keep in mind I am not looking through this camera footage while I'm recording this. Alright, I'm going to try to come back now. Let's turn towards this long open ping. A little more. Oh, too much. Okay, let's wait for the sonar to update. 9 feet in front of me. Maybe I go a little bit. It seemed it was a little more open this way. Let's go forward, see what happens. Okay, I'm getting further away from this back wall. Still seems to be space in front of me. The space behind me is increasing. Okay, something's way off to my right. That might be to the side of the couch. Over in this direction now, to the right is, so I probably have the couch somewhere up here to the right. Let's keep going forward. Oh, I think I might have just heard it hit something in the other room. Let's go a little bit. Uh-oh. A little bit to the left. Okay, there's space this way. That looks good. 11 feet. Let's go this way. Okay. So there's something in front of me. Let's turn a little bit to the right. There should be a pretty long space behind me if I'm facing the right direction down that hallway. Something's timing out over here, so that's probably the couch. Okay. Something's in front of me. I should be most of the way back towards where I started. I only am 9 feet. Well, no, I'm 16 feet on the y-axis. Okay. I'm not getting a reading right in front of me. Am I running into the couch? Let's go to the left. That's a nice long reading for a second there. Okay. Something's in front of me. It's also possible that my values are drifting, especially if I slip over the carpet or something. I don't really know where I'm at anymore. I'm kind of lost. So let's just find an area with pings in front. Let's try that. 10 feet. Okay, now space is opening up behind. Okay. I'm approaching a wall, clearly. I think, and I'm getting to the point that I can hear it around the corner, so that might be my front door again. This display is showing me facing a different direction than I would expect, but now now I have some space kind of over this way. Let's turn this way. Oh. I'm in this narrow hallway, and I can actually see it now. Alright. Yep, I can see it coming back through my narrow hallway. Pings against the walls on both sides, open space behind and in front. And we have made it back. So in the end, we're facing pretty much opposite the direction we started. The Y0 was defined as this way. Yet on screen, my y-axis seems to think it's pretty close to 0 still. And also notice these did not return anywhere near close to 0. It still thinks I'm 15, 30 feet away. So probably what happened is it was trying to rotate, but was stuck on something, or it hit something and slipped and caused it to rotate. And then the dead reckoning on the rotation was completely off, and that would have thrown off the linear too, because it essentially is just integrating the distance traveled depending on the angle. So that probably is what threw that off, but overall we kind of made it back. This is a sped up clip of the robot driving beautifully on its way into the kitchen, exploring around a little bit, and then making its way back until it hits the corner of the couch right there, and you can see it's forced to rotate. It was trying to go straight forward, but in doing so, it actually rotated a little bit and introduced probably 15 or 20 degrees of error between its dead reckoning steering angle that it thought it was at and its actual angle. From the onboard camera, it then gets caught on the opposite corner of the couch somehow. I don't know what exactly got stuck, but trying to just drive straight forward again, here I was only on the forward command, it managed to spin itself a little bit past 90 degrees all the way around the corner of the couch, and then spin itself like another probably 45 degrees until it was pointing straight into the couch. So that, combined with the hit on the first corner, explains how the dead reckoning angle was off by almost 180 degrees. And then from there, the linear aspect of the dead reckoning would have been adding instead of subtracting because of the angle being off. And so that's why it didn't quite get anywhere close to 0, by the time it was finished. I'm going to quickly run through the code. It's all pretty much C++ in the Arduino IDE. I've been through this main one before, but this main program is what runs on that first microcontroller that's plugged into the big 24-pin connector that runs through the slip ring. The new things in here are that I've implemented the 3 rotary encoders, and I have a PID loop running. In the main loop, there are a few things that it does every iteration. Over here under the motor encoders tab, the turret one and the steering one both have some logic that handles the fact that they wrap around a circle in 360 degrees. So that keeps it from winding up forever. When it gets to 360, it clicks back over to 0. I did not do that on the drive encoder because I'm using its accumulating value in my dead reckoning. So what this does is every time it runs, it takes the linear difference from the last time, converts it into an X and Y component, and keeps summing that up and converting it to feet, and then it passes it on over the I²C. For the turret and steering PID loop, this is to match the turret to the steering direction. One of the 16 transducers is always pointed in the direction that it's steering. That also lets me tape a camera on top, which keeps it pointed in the steering direction. Those two things are not mechanically linked, so I do need to use this closed loop control to keep them parallel. It has kind of some similar code that keeps it from going the wrong way around a circle if the set point and the actual value are on opposite sides of 0 from that circle. But otherwise that decides what the throttle should be for the turret motor. I've also added in a couple of functions to handle the I²C communication, and that's really all that's changed in this program. This next one runs on the microcontroller that's plugged into the sonar board. So it has these 4 digital pins that it uses to select which actual transducer is hooked up via the multiplexing. So these are all just either high or low, and based on that it decides which one is used. In the main loop, once per loop, it runs through the circumference of the 16 sonar transducers, goes through all 16 of them, and runs the sonar function on each one. It also sends the data every time during this loop, and it has this short delay. I put that in just to prevent, say, one transducer from still having some lingering echoes bouncing around when the next one starts. So hopefully they never interfere with each other, but I've not really played around with how much of a delay that needs. I may be able to speed it up, or I may not need it at all, don't know. This one has some slightly more complicated I²C code because it is the master, but it's pretty much just sending and receiving to each of the other microcontrollers. This is where the actual sonar stuff happens. So it decides via multiplexing which one it's going to use. It writes the signal high, and then it just waits until it receives an echo, and it converts that into a distance based on the speed of sound. This is basically the truth table that decides, based on the multiplexing, what those 4 values should be to select each one. And of course they're not plugged in that order because the cables are not arbitrarily long to reach any plug, so I swapped the order and accounted for that here. Not a whole lot is going on in the ESP code. It's just connecting the Wi-Fi, and then it's sending all of the data. It receives 8 bytes, which include a representation of which of the 4 arrow keys is being pressed. It's not even using all 8 bytes to do that. And the data that it sends is an array of 20 floats. So that is 16 distance values for the 16 sonar transducers. There are 2 values representing angles of the turret and of the steering. And then there are the X and Y component of the dead reckoning in just Cartesian coordinates. So that takes 20 floats. Also some I²C communication, but that is pretty much it for this guy. This is the processing code which runs my GUI and handles communication between the PC and the ESP. I'm by no means a processing expert. This is kind of the only thing I've ever done in it. Just setting up some coordinates for the different shapes it draws, connecting to Wi-Fi, reading data from the ESP. The business of this kind of happens down here is the complex, tricky part. It takes the 16 values for the sonar distances, and it then converts them into an X and Y component to plot a line just in the Cartesian coordinates relative to that center circle I have representing the robot So that's where it draws the line based on the X and Y component of that distance from the center of the robot. And then it just does a special one in a different color for the steering direction. And that is pretty much all that this guy really does. Prints the dead reckoning values. Not a whole lot to this. Reads the arrow keys that I'm pressing on my keyboard. Next goals for this project is I'm going to fix that broken limit switch, get it to home totally automatically every time. That got really old after doing it a few times. I want to get these bumper pressure detectors working so I can sense when I've actually collided with something. And then after that, I'm probably going to ditch the ESP32 and put in a more powerful microcontroller like a Pi or something. And then I want to integrate it with ROS and use some pre-existing SLAM libraries and algorithms to start experimenting with some simultaneous localization and mapping. So that'll be really cool and coming in the future. So thanks for watching.